everyone, welcome to Gradcast, the official radio show and podcast for the Society of Graduate Students here at Western. I'm your host, Yousuf.
And I'm your co-host, Clifford.
And today we're here with Gavin Tolometti, who's doing his PhD in Earth Sciences. Welcome, Gavin, to our show.
Great to be back once again.
You said it was the third time round.
Yeah, this is number 3. So
Third time, awesome.
Great. So we're hoping to build on it. So Gavin, I don't know if you want to introduce yourself for the third time or if you want to get straight into it. But just tell us a little bit more about yourself to introduce you to the audience again.
Yeah, no problem. So I guess this would be for anyone who's new. I'm actually a Gradcast member for the past approaching about 2.5 years now. I have in planetary and earth science at Western doing my PhD. And my main focus is studying lava flows and impact melt on Earth to try and understand them on the moon in particular, and branching into Martian lava flows a little bit now, which is a new part of my research. And most of it does involve looking at remote sensing data sets, which what I mean by that is like imagery collected by satellites and planes on Earth and planetary ones that are currently orbiting the moon and Mars, because it's one of the best ways to get a large overview of the surface of different planetary bodies. And it's the best way for us to try and understand features that we see on the surface of the moon and Mars by studying similar ones that we can actually go to physically on Earth. It's like a comparative study, trying to understand what we see on Earth to try and understand what we can view via that imagery of the moon and Mars, but what we can't physically touch.
So I guess you collect a lot of data and you explore yourself to different sites, volcanic sites perhaps on some locations that you might want to share with us.
Yeah, definitely. So the first site I visited was, and I actually talk about this a lot in the second time I was on, is that Craters of the Moon National Monument and Preserve, which is one of the largest lava fields in the United States, the mainland not including some of the other areas like Hawaii. But it's a very unique lava field because there's so many different types of lava flows, not just the typical ones you probably see on the news when Hawaiian volcanoes erupt, where you see this very smooth, glassy flow known as a pahoehoe, or this very rough, razor-sharp, jagged lava known as an a'a. But this lava field hosts numerous different types, some built of giant plates, some have slabs that have been broken into pieces, some look like rubble, similar to what you see at construction sites, like all the material that's been dumped that looks like small and big pieces of rock. So I started looking at that site because it has unique surface properties, or in particular, like the roughness of these lava flows. They show some similarities to lava flows on the moon. And what I wanted to do was to use remote sensing data, which is available on Earth and also available on the moon, to try and see if we can understand about the lava's properties, but only using the remote sensing data. But I did have to go travel in the field to ground truth this type of remote sensing data, because just because we can look at this imagery, we still need to be able to ensure that we understand exactly what we're seeing. So that's the one advantage of going to these sites on Earth, since we can look at what this remote sensing data sets are telling us just by sitting in a lab. But then we can go in the field and we can either confirm or reject hypotheses we have based on only that data, which is very handy, because if you don't do that before looking at planetary data sets, your whole ideology of what you might be looking at could be completely different.
Mm-hmm. And I think it's very interesting how you brought up the Hawaiian example, because I think to the unaided eye, a lot of people would say that lava has almost this mythological presence, that it's been embodied in cultures for thousands of years, and has that it as a sort of natural tour de force, as you will. So why do you find an attraction to lava? What importance do you see in studying its properties, especially when it breaches the surface in a lava flow?
I think for me, well, in planetary science, lava flows are one of the best ways to try and understand what processes might be happening within the center, not necessarily the core, but like beneath the surface of a planetary body. It can tell us a lot about volcanic eruption styles, which can then tell us about the magmatic processes that are currently happening in the shallow region of a planetary body. And also, they become very useful because, one, they do pose as a hazard for astronauts and robotic missions. You need to be able to understand what exactly you're landing on. And lava flows are notorious for being very either razor sharp and glassy, or they could have very thin shells that actually have giant voids beneath them. So if you were to land on it, you could fall through a ceiling, and you've just lost your transport or your lander at that point. And for me, I just think they're very cool and interesting to study because it's molten rock that's managed to reach the surface of a planetary body, flowed for a certain distance, and then solidified. So it's just so cool to be able to look at them, at least what they look like after they've solidified, and try to deconstruct the story from only what we can see and not always because we never get to see what it's like at the flow, unless you go to, if you're very lucky, you go to Hawaii, or in some places in Iceland, you can see these flows active, and then you can study them as they develop, which is useful. But most flows, especially on the moon, we never got to see them because most of them stopped erupting 1 billion years ago. So all we have is whatever's been preserved. So we want to be able, so it's so cool looking at what we can see and try and deconstruct it and trying to create a story from that.
So Gavin, you're very lucky that your PhD work requires you to often visit these beautiful sites and travel a lot. I wish I could do that as well. Well, I mean, I do go to conferences, but I mean, I study philosophy and I can't do much about studying abstract objects. I can do it over here sitting on my sofa. So you're very lucky. Is there any location site that you really enjoyed and learned a lot, especially when it came to know more about the morphologies and the surfaces of Mars or the moon?
Yeah. Well, so what for that question? It pretty much leads to the follow-up study after I completed my work in Idaho. It was last summer actually, in August, we traveled to the Central Highlands in Iceland, where we got to visit a lava field that erupted in the end of August, literally quite at the end of August 2014. And it was erupting for about 7 months until the end of February. And it was interesting because, one, it's the largest flood-style eruption that's happened in Iceland in the past couple centuries. And what I mean by flood-style or flood basaltic volcanism is that usually what happens is a crack would open up on the ground and the lava will spew out and start to flood on the surface instead of creating giant cones and erupting from this cone, similar to like in Hawaii. But this lava field was unique because it erupted in a glacially active area. It also redirected a river system when it erupted, completely blocked it off, and then the river split and started to flow around it. Created these temporary hot springs, which could potentially have created areas where microbes could have been able to survive and thrive. And it's also got morphologies and roughnesses that are similar to Martian lava flows that have been studied using imagery collected by the Mars Reconnaissance Orbiter. So I was actually really excited to get to go out there, not just because to see the lava field, but it was also my first time getting to go to Iceland in general. And there's a reason they do call that country the land of fire and ice. It's very bizarre walking on the lava field, and you can still feel the heat coming out of it. That's why it may have been 5 years since it erupted, but you could still feel the residual heat coming off of it, so it's still quite hot. And then in the distance, you just see a giant glacier that's just looming over it. So it's just very weird seeing something that's extremely hot next to something that's extremely cold and then coexisting.
I had no idea that would be the kind of sensations you would feel even after 5 years. That's super cool.
Mm-hmm. Quite a paradigm shift to have two completely opposite forces of nature side by side, which again the nickname for Iceland is so apt in that regard. So Gavin, in your experience, how large are these lava flows? Like, are we talking tens of kilometers large? Do they vary based on how much molten rock is spewing out of the Earth's surface? What kind of dimensions are we talking about?
It definitely varies depending on the eruption in general. In volcanology, there's two types of eruptions. You either get an explosive eruption or an effusive eruption. The ones I look at are effusion, which just means there's not really much gas being released. It's mainly just lava being spewed out of a volcano cone or a crack in the ground. And explosive ones are, I guess, a lot of people are probably more familiar in North America to mount the eruption of St. Helens. That was an explosive eruption. The Iceland volcano that erupted in 11-12 that disrupted airlines around Europe and the North Atlantic, that was also explosive. And they're actually the most dangerous ones because, one, they can decimate cities if it's big enough. Pompeii is the biggest example for that. While effusion ones, they can cause destruction to civilians and towns, but only if you're close by. And they can release a lot of fumes, but not a major amount, at least not the ones that erupt nowadays. I say size-wise, the one in Iceland is about in the approximately tens of kilometers in size. But there have been ones in the past that they go to like the hundreds of kilometers in size.
Wow.
But what's very interesting, though, is that if you compare them to the lava fields that you see on the moon and Mars, ours are extremely tiny. What we could consider maybe it's 10 kilometers squared lava field here, you can look up to maybe 1,000 or even more kilometers squared on the moon and Mars. They cover vast areas up there. And part of that's just mainly might have to do with like what's actually happening and what was happening if we're talking about the moon, what's happening in the interior. So it might be a completely different process, mainly because it's a smaller body, the heat source is smaller, or there just might have been some forces that are happening in the moon that weren't happening in Earth and vice versa. So it was able to spew all this lava out. So there are big size differences, but it mainly depends on how much magma is actually being forced up to the surface.
Awesome.
Very interesting. Very interesting.
So you had a couple of presentations this summer. Can you tell us more about those conferences and what you presented on?
Yeah, definitely. So this year's probably is probably the most conference heavy year I'm going to have, mainly because since I'm approaching the final year of my PhD, it's the time where you really need to start networking and meeting people to apply for postdocs or jobs in the future. So the first conference, I went to two in July. One was the Loon GradCon, which is it's a small conference where graduate students and postdocs present their research, anything to do with lunar science. To one, you get to meet other people in your field, and two, it's your first chance to network with professors that will be attending. The one after that was the NASA Exploration Science Forum, which happens every year. This one was virtual, unfortunately. But this is where I got to present my Iceland research, and I got to talk to a couple of professionals who got to visit my poster at the time to try and get ideas about how I could maybe move forward with the results that I have, get new ideas for new projects, or just a chance for me to practice presenting this work. So those were the main things I got to present at those conferences this month.
I have a follow-up as well. So given COVID-19, so you recently had a virtual conference as well, but I was thinking about the sites that you were previously visiting to collect data and stuff. How has COVID-19 impacted your research or what do you think may have to change in the coming months, for example? Are there some worries for you?
Well, when COVID started, I already started to think that all the fieldwork we had planned this summer was probably either going to get postponed to next year or maybe canceled indefinitely. Unfortunately, because originally we were supposed to go back to Iceland in July to do some more follow-up work, and then I was also supposed to go to Labrador to look at an impact crater in August, September. But unfortunately, we had to push those expeditions to the end of next summer. So it's going to be interesting next year because I'm going to have to be finished submitting my thesis and then heading off to the field. So it's going to be a very busy summer next year. But the writing and the remote sensing part of my research didn't really get affected that much, since that can also all be done on my computer and in the lab. And I managed to think ahead enough that I remotely connected my laptop to my lab computers, so I could still, as long as I had internet access, I could still connect to all the programs I needed. So COVID kind of, one part of the research COVID didn't really affect. It made it a little bit frustrating if the internet connection was bad, so then processing takes even longer. But then it was also really frustrating that everything we had planned to build up papers I'm currently writing or to submit new ones has to be postponed for a year because we can't currently use air travel.
Yeah, and if it's any solace, I assure you that you are perhaps not the only one whose plans have been folded as a result of the virus. Now, considering you're coming towards the end of the PhD, do you have an end goal in mind with your research? I know you talk a lot about the lava flows and how they can influence, planetary travel, going to Mars, going back to the moon, etc., etc. What does this mean for the general public? What sort of message can you transpond onto them as to why this is important?
That's actually a question I get asked quite a few times, especially in outreach. So this is kind of the way I like to phrase it. With lava flows, the more we study about lava flows, if we particularly focus on the surface roughness on Earth, it's not as important since it's easier for us to be able to see them, and we know, like, okay, that's very rough and treacherous, we're not going to go near it. Planetary science, they rely on it more because since we can only look at remote sensing data, and if we're lucky, images from the Apollo missions, we need to know exactly how hazardous or rough the surface is in areas, or else missions can't go ahead in certain areas. On Earth, how I talk about my research to maybe the general public is the types of data, especially the remote sensing data that I'm using, has a very interdisciplinary use. That lava flows is just like the focus of the data, but it's not limited to that. Like one of the remote sensing data, as I should have said this earlier, was I use synthetic aperture radar. So when everyone hears radar, we always think about when planes and boats use them to detect objects. That is Doppler radar. The synthetic aperture radar creates images from radar signals that strike surfaces and are reflected or scattered back to a receiver. So it kind of creates pretty much just an image you can overlay on top of an optical or visible image, and you can sometimes see structures that you can't see with the naked eye, such as some slopes will be very bright because it's bouncing right off a steep cliff. Anything that's got a lot of giant boulders or raggedy material, vegetation, that will appear very bright because it's been able to scatter these signals. Or when you have flat surfaces such as roads, still water, it's going to become back very dark because, again, the signal's just bouncing back and there's not really much scattering going on. So, but that data is constantly used nowadays to monitoring ship movements in harbors, looking at deforestation, and because if you look at it annually, you'll be able to see areas that probably shrink. It can monitor agricultural growth and degradation, the expansion of the growth of deserts, which is becoming a huge problem in some parts of the world. And you also use it just to monitor volcanic activities on Earth. They can be used to let you know, like how much area did the lava flows actually cover? Are there areas that we think it might be safer for people to go to if eruptions were to happen? And also it allows us to monitor glaciers as well. So synthetic aperture radar is really good at monitoring sea ice growth and recession. So we're actually able to monitor glaciers in the north, in the Arctic and in the Antarctic using this data set, because sometimes if there's clouds, we can't see through clouds, but radar can go through clouds. So it's good all year round. It doesn't rely on light. So you can even do it 24/7, unlike a normal camera. So that's why I like to sell that to the public, because even though lava flows may not particularly connect with them, the radar aspect of it can. And that's why I really love using it in planetary science, because not that it hasn't been used for the past couple decades, it still has some steps that need to be taken to properly understand the data. Because there's not many professionals that have a full-on focus on this type of radar in planetary science. There are quite a few, but not as many as I'd I would say, as other data sets such as infrared, UV, ultraviolet light, optical imagery, and even ground penetrating radar is probably has a bigger field than synthetic aperture radar.
Mm-hmm.
Wow.
No, and it is a lot, but I think it is very interesting how you draw the link between how we can utilize radar to monitor the shared burden of climate change that's currently undergoing on our planet. Now, can the average Joe, the average tourist, visit these lava flows? Is this something that's off limits to normal individuals, or is it reserved for particular ones? Hoping that the Hawaiian or Icelandic tourist board sponsor me with this question.
Well, the good thing about the Craters of the Moon in Idaho is a national monument. That's open. That's part of the United States National Park Services. So they're actually there. They had to give us permission to go to some areas. So that's open to the public. We always constantly tell people. The one in Iceland actually is open to the public. You can't go in the winter because since it's in the highlands and it's 3 hours off the main roads.
Wow.
They close it off in the winter just because you physically can't get there. You do, however, they do give you lots of warning. We had to rent. I will say this though. I was in charge of logistics that year because my supervisor was on maternity leave at the time, so she put me in charge. And I had to find the right vehicle to book to, one, deal with rocky terrain, harsh conditions, and capable of driving through a river.
Wow.
So, yeah, we had to drive through 2 rivers to get to our campsite. So I had to make sure that the clearance was at least 200 centimeters above the ground. No, not 200 centimeters. That's a lie. About 200 millimeters off the ground. The vent was not so low that water could easily get in, because as soon as the water gets into your exhaust or your vents in your car, floods and it stalls.
Not good.
No. So after dealing with that and having a very unpleasant experience with Enterprise, because they promised me a vehicle that was big and they gave me one that was about 2/3 its size.
It's not acceptable.
No, because they claim it was in the same class as vehicle, but it's only because it costs the same, but necessarily its performance is the same. But anyway, you need those types. You need to pretty much get a big truck. You can drive there, go through rivers. There's a campsite. That's where we stayed. It's right at the base of a caldera. So an old collapsed volcano. I think the last eruption there big one was 1878.
Wow.
And it's got a lake in the center, which is beautiful. Around the area, if you dig, depending on the time of year, if you dig around some of the soil, you can find ice that's buried because it's still freezing cold in the ground, even in the middle of summer. And what was also really cool about this location is one of the sites that America sent the Apollo astronauts to train before all the Apollo missions began.
Interesting.
So I actually got to see some videos of Jack Schmidt training to be a geologist, being a geologist in the field, training to be an astronaut.
So, Gavin, thanks for sharing this entire new world for many of us, at least. It's super fascinating, and I have a couple of tangential questions. So the first one is, given that you're so interested in volcanic flow, I was wondering if there's a movie recommendation that you might have for people who might be interested to have some idea of what you're really interested in.
Are we going with realistic or just plain whack?
You can go for both. You can give me 2 movies. One off the charts, it's super cool but makes no sense.
I can't think of a movies that are entirely accurate. I know one movie that comes to the top of my head is Dante's Peak.
Yes. Oh, yeah.
That is supposed
memories.
to be that is supposed to be based off the eruption of St. Helens. I actually quite enjoyed the movie. I know it's available on Netflix. Oh, if I was to give another one, there's not really any. I know there's the movie Volcano. I've never seen it myself, but I think if you want something wacky, completely inaccurate, but probably it's just fun to watch because it's so dumb, I'd recommend that. It's apparently, as far as I know, it's like a volcano just appears in the middle of a city and then erupts. So it kind of just hurts my brain thinking about that. But
it could happen. You don't know. No, I'm
I don't want to take a chance.
And
well, those are the two movies I say I definitely would recommend.
my other tangential sort of question is, you when I first came to Gradcast as a guest, you and Ariel had interviewed me, and now I'm interviewing you. So this is kind of cool for me as well. I wanted to know, for how long have you been on Gradcast, and also what have you enjoyed most being a host and producer?
So it's been about approaching 2.5 years now. So it's been a really good experience. I mean, from hosting, getting to talk to other students about research topics that are not in my field at all. So for me, it's like always learning something new. Even if I only take one thing away from an episode, it's still something I can add to my own, almost like my own directory of information. It's just, I get to learn something that one, maybe is very bizarre, very unique, very weird, very complicated, or just plain right ridiculous. But it's something I got to learn outside of my field, which I always seem to appreciate quite a bit. And it's also given me more of a chance to talk about not even just my work, but trying to communicate with other students and professionals in different fields in a not using simple language, no jargon, and trying to stick to layman's terms as much as possible, which I think is very important and something I think is a skill that's not being refined well in academia or even industry. I'd say academia and industry is a skill that I think we need to develop more, because there are still times where I'm sure we've all experienced it if we go to some meetings or conferences, that you get some speakers that are really good, you understood everything they're talking about, but then you get others that either are droning and you have no idea what they're talking about because they're talking in a language that only they can understand, or they're talking in a language that only people in their field would understand, which I think people need to know when to switch that on and when to switch that off.
Yeah.
So that's something I've really gotten to improve on ever since joining.
I think that's a very good piece of advice for prospective academics or podcasters in the future. Now, Gavin, it looks like we're just about out of time. Just want to thank you very much for coming on yet again, and we will be working with you soon.
Yeah. I guess just we wanted to know if you wanted to share your social media information for all of us to contact you.
Yes, so I'm quite active on social media. My Twitter handle is @GavinOnTheMoon, and that's also the name of my Wix website, Gavin on the Moon, PhD research blog. And I am on Instagram. I've recently started to get into, completely off my research, getting into cooking and baking. So I have got one account called the Lava Chef. Yes, I had to plug lava in. I had to think of something. So I thought that's going to be perfect. And no one took it. So I immediately jumped to the opportunity. So I'd say, yeah.
Awesome. Yeah. So yeah, thanks for coming on our show. And this has been Gradcast, the official radio show and podcast of the Society of Graduate Students at Western University. I've been your host, Yousuf, and my co-host was Liam Clifford. We've been speaking with Gavin Tolometti, and this episode was produced by Ariel Frame. If you would like to be involved with this show or get in contact with us, email us at gradcastradio@gmail.com. You can follow us on Instagram, Facebook, or Twitter at gradcastradio. To listen to us, we are on the radio at CHRW 94.9 FM. You can also find all of us on our episodes on our website at gradcast.ca or on podcast apps like Podbean, iTunes, and Spotify. Alternatively, select podcasts have been uploaded to YouTube at Gradcast Radio. Thank you for listening and have an awesome night.